One job is
for $20,000.
All right, we might get underway. Thanks for coming to our April presentation, which I suppose we organised a little while ago.
Yep.
I suddenly realised that Andrew, actually it was the open day, wasn't it? Open day? No. Anyway, it was something. And Andrew, I suddenly realised that Andrew worked for this fine organisation, and I went, that'd make a good presentation night. So we got Andrew along. Now Andrew's had a long and illustrious career.
It's one way of putting it. Varied, I think, is another.
Well, which included, and I'll get Andrew to expand on a little bit, but included a stint at CERN, at the Large Hadron Collider. So has some experience in some very interesting environments. So without further ado, I'll hand over to Andrew. Thank you.
Thanks. So this is kind of a bit of a rambling talk. As normal, I left it till the last minute before sticking a whole bunch of slides together. So feel free to stop in and ask me any time, any questions. So a bit about me. I started using Linux about Kernel 2.0, so I finished uni, got a job, went back to work for the lab, hopefully in theory to get a PhD, but ended up doing a lot of sailing. And then we had to glue together the PCs in the lab that were connected to the instruments, the Mac that my boss used to do all his papers, and then it was like, how do we join these? So at the time it was like, oh, this Linux thing looks cool, and kind of got into it. And then realised that doing bioinformatics and working on the computer side rather than doing enzyme preps in the cold room was more enjoyable, and got into computing. So that's kind of my history. I have a vague plan for tonight, which is a bit of rambling about what is supercomputing over normal, types of systems that we've got, high performance, high throughput. There is a difference between the two, and I'll try and explain it. Sometimes it's referred to as capability versus capacity systems. The high performance ones normally have fancy interconnects that cost you money, and you need a lot of extra bits as well. Typical users of these are biology, doing protein folding type simulations, genomics, lot of running DNA databases and reassembling things. Astronomy, which I'll touch on, especially because the Pawsey Centre for Supercomputing, for radio astronomy, and obviously weather uses a lot. The other big site that publicly has large crays in Australia is the Met Service, the BOM. They've got a couple over in Melbourne. I'll very briefly talk about radio astronomy, Joseph Pawsey, but it's not my field, so please don't ask me any technical questions. Okay, the misquote from Thomas Watson, there's a world market for made via computers. Supercomputing feels a bit like that. It's a bit like Rex. The number of supercomputing sites is probably on a par with the number of people who are doing EME bounces. It's a very small community, you all know each other. You're only as good as your last mistake. Everyone knows you. It's useful and terrible at the same time. So early computer systems need a lot of hand-holding, few installed, lots of surrounding infrastructure. From an HPC side, not a lot has changed. They still need a lot of hand-holding. They're a lot bigger, more powerful, but they still need a lot of support around them. Seymour Cray, I happen to be wearing a Cray 2-ish t-shirt. This is from Seattle. But he was designed the CDC 6600, which was kind of one of the first supercomputers of its time. It wasn't known as such, but he came up with this: anyone can build a fast CPU, the trick is to build a fast system. And that link of overall performance is critical. It's like, yes, you can have good bits, but when you're really pushing boundaries, you're let down by your slowest part. And that's what makes it hard. So the classic Cray design is this Cray 1A. Historically, if you think of a supercomputer, you think of one of these. The circular shape was because each cable was under 4 feet, and so to be able to run the cables between any part and any other part, you had to have this circular design. The base was cooling and power. Even the under 4 feet, you still had 50 miles of cable in the damn thing. It weighed 5.5 tons, 115 kilowatts of energy, and there was 116 megaflops. So we'll talk about flops in 2 slides, which is basically floating point operations per second. It's the benchmark we're using to rank systems against each other. Classic design, it tends to be used in movies somewhat. Bonus points if anyone can identify this film. Sneakers. One of the best hacking films about. Sorry. So, going through what the floating point per second is. So, the earliest example I could find that someone put a figure on was the Apollo guidance computer. So this was 12 kiloflops. There's commas for decimal places in here, commas in as well as the units. So, although it's 12,000 flops, it's 12 kiloflops. The AGC also is 32 kilos, which is remarkably lightweight, and only used 55 watts. For 1966, that was pretty bloody cutting edge. 97, Deep Blue was publicly like the first probably time people thought of supercomputers in the general media when it beat Kasparov. So that system was 11.8 gigaflops. So we're up factor of 1,000 already. We've gone from kilo to giga. My first supercomputing system that I worked on, HPCX, this was at the UK Supercomputing Service, was 28 cabinets in a room, each 19-inch or 24-inch racks for IBM. Each rack was a single 32-core CPU monstrosity, vast amounts of energy needed, and gave a whopping 11.83. Gave a whopping 3 teraflops. It came in at number 9 on the top 500, which I'll talk about in a minute, and lasted on that system. When you're on this top 500, it's basically the ranking system that they all beat each other against. The lifetime of being on that chart is really small. If you want to play now, the current top system is Fugaku, which is nearly half a exaflops, 442 petaflops, vast system. Magnus, our current system at Pawsey, is 1 petaflop. We pull about 697 kilowatts when it's running. That's just for the computer. That's not the ancillary, the disks, the login nodes. That's just the main chassis. So we came on the top 500 in 2014 at number 42 with that, and we dropped off after the June 2019 list. We were down at 453. So same system, but new fancy ones that's more efficient have overtaken us.
And that last one on the list, the 442 petaflops.
Yeah.
That is 30 megawatts.
Yes, that is 30 megawatts.
Flippin' heck.
Yeah, this is a problem big sites have. I'll briefly talk about it when we talk about our new one. So we've got to upgrade our power at Pawsey to put our new system in. I think NERSC, which is the American lab, they've got an XC40 system, which is some GPU, some CPU. But from memory, it's about 16 megawatts. You're talking megawatts for any big system now. It's not something you run in your shed. So our Cray was one petaflop, but when you compare Deep Blue or HPCX, HPCX 2002, 3 teraflops, an iPhone 12 is 11 teraflops, battery powered and fits in your pocket. It's the Moore's law. Yes, it's good for CPUs, but it's the whole surrounding thing. And I'm not going to discuss how we're probably hitting Moore's law limits. So giga 10 to the 9, tera 10 to the 12, peta 10 to the 15. The big push now is for exaflops. So when I talk about the new architecture for Setonix, it's using the same architecture the big American labs have committed to buying. So they're aiming for exaflop scale machines, so double the size of Fugaku, but hopefully not double the energy bill. Fugaku is still number one. The November table came out, and they're still up there. Hopefully this will work.
Time. What did you shoot today?
Oh, I don't keep score, Judge.
Oh, well, how do you measure yourself with other golfers?
By height.
So there is an HPC something waving contest every 6 months. This is equivalent. It's the top 500 is a benchmark site. You run LinPack, which is a linear algebra problem solving to get most number of things. So each vendor will put a big system in front of the customer, and then they tune the algorithm saying how much bandwidth it goes this way and so on to try and get the highest score. It's mostly dominated by the big national labs playing off each other. China had it the last couple of years. When I was younger and sort of getting into high performance computer, the Earth simulator, the NEC machine, sat there for years. It was like something like 7 runs of HPC. It just beat the American labs completely. So current top list is Fugaku, 2 in the States, 1 in China. It doesn't have every site. Obviously there are going to be sites that don't have any details publicly. There may be a commercial decision. I know that there is a big HPC cloud provider in Perth and Texas, down under Geo. They have blooming powerful systems, but obviously it's commercial. They could probably beat us if they wanted, but we don't know. Or there may be a personal choice. One of the big American labs, Blue Waters, the directors said, no, I'm not running a benchmark because it attracts the wrong type of codes. He knows he can fill his supercomputer regardless of how published it is.
Presumably the military stuff as well will be similar.
That's what I meant by classify. Yeah, I'm sure there are sites that have large systems. So you don't have to necessarily go to a vendor. You can build it yourself. They're commonly known as Beowulf clusters. This is a Wired article from 2000, but basically you take off-the-shelf systems and stick them together and you have a supercomputer. You can do it very basically. This is this is the basement in CERN. They used to do this originally with their clusters. Before there was a premium on rack-mounted kit and you had the space, you could get commodity computers, stack them up with circuit boards. You don't need monitors, display, CD drives, network boot the lot, and you have a system. Gave them a very cheap base to get started, and if you're doing high throughput, which is the capacity computing, all you care about is if it's trivially parallelized, we just add more boxes. You don't need that interconnect to get one big system. Been there, done that, got the t-shirt. This is Epic. This is a container-based system that was one of the early Pawsey. Pawsey used to be known as IVEC, and this was down at Murdoch University. 2 containers. One contained the computer itself. The second contained the chiller and the plant room and so on. And this was an HP system, which is why they look fairly similar. So near the front, you've got the disks. Then it's lots of blade chassis. They were InfiniBand connected between the computes, which I'll talk about a bit later. But basically, you can pack in a lot of compute into a container. HP called it Pod. Sun had when Sun was Sun, had a name for it as well. And there are photos, if you look on YouTube, of Google's data centers, which is basically a shed filled with containers. If you're doing that, you don't even need to bother with properly racking them. This is a Google data center. If you're hyperscaler, which is the really big boys, they don't even bother with the shade. You get a very If you're ordering thousands of nodes from a vendor, you get them made how you want them. So these are just designed to fit in, very simple. From memory, I think these are probably the ones that have the battery on board. So rather than worrying about fancy UPSs, you just stick a battery on each box and slide them in. At this scale, you don't care about individual nodes. You care maybe about a rack granularity. Is that system up? And then you start worrying about, is a data center room your limit of how you worry about things being up and down? So this is a Google photo. It's actually a photo of a photo from the Science Museum. This is OVH, similar sort of design. They tend to build their new data centers with a central void, so they rely on free cooling. So you draw the area on one side over the machines and out. So you basically have a square box data center that's only one room thick and rely on the convection. It's a great idea in theory. Sometimes it goes a little wrong. This was about a month ago. The data center in Strasbourg caught fire. Yeah. So the cloud is great. It's someone's computer until you have everything in one cloud region. They have multiple regions for a reason. If you're worried about data, make sure you distribute it. So, got a lot of boxes. What else do we need? So you've got your code. You want to optimize it within each node, server, box, however you want to describe it. I'll talk about nodes here. If you want to connect the nodes together, you probably want to interconnect them somehow. So I'll go on to that shortly. You need some sort of storage. Most servers at this level is basically a motherboard and memory, and enough disk to boot it, possibly. You may not even do that. You may network boot them. You've then got to have storage for your data, storage for your software, somewhere the users can log in. Can they actually submit jobs? Can they interactively work with the system? Can they visualize the results? Do you have decent graphic cards? And the software itself, you've got your application software, the code you want to run. How do you compile it up? Have you got compilers that are optimized for big systems? Numerical libraries. Have you got a good maths library that's really tuned for getting the last bit of resource out of the latest cutting edge chip you've bought, and then you find it's not supported by a compiler and you have to go back. So, or it's buggy and it's not as performant as it should be. And obviously you need debugging. Debugging one system's okay. If you're debugging a job that's running on 500 nodes, it's more challenging. So each server, you've got your farm, you've got a cluster of servers. Each server probably has 2 sockets at least. Each socket has got multiple cores. If you're Intel or whatever, you've got multiple threads. And how can your application really make use of this? Because you want to get as much as you can for that. And of course, each of those, you've got different memory caches, level 1 cache on the die. Every time you go to a different layer of memory, you're taking a massive hit in performance for getting the stuff back. If you're running your spreadsheet, you don't care. If you're running thousands of nodes, you really do care about this. And that's a whole different skill set. So how do these talk together? We have MPI, which passes messages between processes. OpenMP between machines. Is that right? I always get this wrong. They've got message passing, MPitch. There's a whole bunch of standards, and like the traditional XKCD cartoon, it's complicated. How you optimize, which one you use. So the Crays are based on MPT. He thinks, yes. But other codes may come in with OpenMP, and you have to recompile, and then you've got different versions, and so on. This slide is a couple of years old, but gives you a typical idea of latencies going from nanosecond for the level 1 cache to 3 seconds, and these are how close they are to the core, and they're tiny, relatively. Memory on a node's probably 64 gig or so on the computer, but then you've got, if you need more than that, you go to storage, which maybe on an HPC system you're probably talking maybe a couple of terabytes. The hard disk drives a couple of petabytes, but you're going to hit slow speeds. So Ethernet is standard. I mean, 1 gig, 10 gig, that's pretty much expected on a box you buy. For any server class machine, you go to Dell, you order one, that's what it'll come with. 25 up to 200 is off the shelf. You say probably up to 200 gig network on a server. Your core networks, maybe more. I'm looking at network people. 400 gig-ish, yeah. If you start wanting anything fancier than that, the switches are getting really expensive and the optics aren't cheap. And you're going to have some latency between the nodes. Ethernet's good, but it's still in something milliseconds. InfiniBand, which is now being bought by NVIDIA, Mellanox is a main player in this. 200 gigabits, low latency because you're actually able to remotely DMA access one node to another over the interconnect. So it's great in a trusted environment. Doesn't work when you've got multiple users with root access on the system. So for a closed ecosystem like an HPC system, it works. It's not something you'd have in a commodity system where you've got shared tenants. It's doable, but then you're talking containers and another layer of abstraction. Intel for a while had Omnipath. They bought QLogic, which was one of the InfiniBand companies, promised a few things, and it died a couple of years ago. We have an Omnipath switch. How you connect those, the topology for getting one machine to talk to another when you start connecting them together. The main ones at the moment are Fat Tree, Taurus, and Dragonfly. So Fat Tree is basically hierarchy of switches. You know, however many you need to get from one node to another, how many hops it has to go through. Each of these adds a bit of latency. Number and bandwidth, the faster your checkbook, the bigger your tree can be. And that's about it. You often use commodity kit. The same thing applies for InfiniBand. You know, you can just do with this Fat Tree. But if you're buying big director switches, they're not cheap. If you're just going top of rack switches, yeah, they are, but then you've got the trouble of hop to hop and how you do. InfiniBand is, to do it properly, instead of it being discoverable, basically each node that comes up gets an address and it knows the mapping arrangement from one node to another. So it speeds up that way. The Taurus network is exactly that. It's like basically three-dimensional torus between the nodes, so they can work between them. If you've got some codes that only need to talk to near neighbours, this is fantastic, but you're then back in the specialised hardware region. This was popular early 2000s because we had things like the QCDOC. This is a machine I had at Edinburgh. The bottom right-hand picture is a colleague. The main two systems here are at Brookhaven Lab. So the three systems built, each of these was 14,000 CPUs. So we had one in Edinburgh, a production system for researchers in BNL. Is this a freebie? Yeah.
It is now.
And if you look at the board that Cray's pulling out, basically what we had were two low power custom ASICs on a daughter board, 64 daughter boards on a card, and that slid in, and then the back was this rat's nest of like custom cabling. But that design worked. That was very much a one-off laboratory based project. But then IBM came out with the Blue Gene machine, which was basically a commercial version of this. And they did 3 iterations. The Blue Gene L, which I think is this picture. There's probably a Zargon, which had just a more polished thing that didn't involve several research students to keep it operational. And then we have the Dragonfly. This is the current Cray chip we have, Cray switch we have on the system at Pawsey. Aries switch is great if you want to connect any number of systems to each ASIC, providing it's 16. So it scales, sort of. So there are 4 nodes on a blade with the switch chip at the back. If you want to have interconnects at the front, you only put 2 nodes in, because then you need the other 2 nodes to talk to the front panel for your PCI card. So yes, it's flexible-ish. So most of our systems have 4 nodes in, the 4 compute nodes to a blade, apart from the I/O ones, which only have 2. We have 16 blades in each chassis, and then 3 chassis per cabinet. So basically 6 chassis is a rank 2, and then you have optical cables between cabinets, and that can extend out. Which brings me on to day job. So Pawsey Supercomputing Centre was a 90 million infrastructure investment by government in 2008. Basically, after the GFC, they funded it. It's in Western Australia, and it's one of the 2 supercomputing centres available for academics. So NCI in Canberra, based at ANU, is the current one, was the current one, and then Pawsey has our systems we'll talk about. So at the moment, ANU have a more powerful system than us, but we'll beat them soon. We've just had a $70 million capital refresh project that's going through. So when I talk about some of our new systems, I'm going to be deliberately vague, because I've just gone from what's on our public website. That covers me for anything that I've got with vendors. So it may be vague, but it's easier that way, I'm afraid. So Pawsey was a dedicated centre built in Kensington. It's designed as a lights-out data centre, so we have an exhibition space at the front, but everything can be done remotely, hence why I'm in Tasmania. Named after Joseph Pawsey. We have 3 rooms in the data centre, 1 large hall that houses a supercompute, 1 that houses all our network gear and disk arrays, and 1 that houses a tape cell. We still use a lot of tape in computing. It requires a minimal amount of power to keep operational compared to spinning disks. And it's got a good lifetime. Yeah, for the capacity it's relatively cheap. So this is a really bad photo, basically about Joe Pawsey. He's born in Victoria in 1908, did some very early work, and interferometry is kind of the main bit he's remembered for, which has significance when we come to the telescopes later. So Pawsey, as it stands, we have about 1,600 users, over about 190 projects using our system at any one time. Principal researchers submit an application saying, I have this scientific proposal, it requires X amount of time, I need these resources. There's a call out at the end of every year. We've just finished one just now for next year's allocation. And we say, they're all ranked by peers who basically go through and work out, yeah, we like your project, but that's no good, or no, it doesn't meet the criteria. We're about 100% oversubscribed for people requesting resources versus what we have available. When we say resources, we tend to work in allocation of a CPU hour. It's about the most flexible way we have of saying how much time people can get on their system. So if you take a node on Magnus, they have 24 CPUs, 24 cores, so 2 times 12 cores CPUs. So if every hour that you run a job on a node, we charge you 24 units. So this photo, we can see our main systems here. We've got Magnus, our current production Cray. The one behind is Galaxy, which is dedicated for radio astronomy. It's an old photo, so the 2 Cray cabinets are basically logging nodes, and the interconnect switch, and that's replicated at the back for a second stack of login nodes and a second interconnect switch. The Cray system themselves, picture on the left is our test and development system, which has a single chassis. So The cabinet has 3 chassis, 1, 2, 3. In the middle they have a control board that basically brings up the cabinet. So our test development system is 1 chassis turned the other way around. So the boards slot in horizontally on this one. Sorry, no, they slot in vertically. I must have turned the photo. I've turned the photo. So on our test machine they slot in vertically, production ones they go horizontally. One's air cooled, the rest are water cooled. And so an older picture, because it still says IVEC rather than Pawsey. Magnus is basically 8 cabinets. Cold air comes in at the left-hand side. As a precondition, to cool any room temperature if it was too hot. Goes through a fan, 2 cabinets, another fan, another 2 cabinets, another fan, another 2 cabinets, another fan, another 2 cabinets, and then blown out the end. Because we have a lot of water plumbing in the back, at the end of each cabinet there's a radiator, so hopefully it brings the temperature back down and we can get the heat generated by the system into the water. So Magnus is 600 kilowatts. It's quite a lot of heat to get rid of. The nice thing is, because it's water cooled, that you don't need screaming fans. Yes, we have big fans with the airflow, but that's just blowing over them. The engineering that goes into this is quite impressive. The heat sinks get smaller depending where the blade sits. So on the top of each CPU, although I said there were 4 nodes, the left-hand CPU has larger fin spacing than the right-hand one, just because of the airflow difference. The little details appeal. So Magnus is the general purpose one that most of our researchers use. It's about a petaflop. Galaxy is the smaller one, it's 3 cabinets, and that's dedicated for radio astronomy. So that's mostly used by ASKAP, the Australian Square Kilometre Array Pathfinder. There was another big radio astronomy group, MWA, but they did have a small cluster of GPUs inside this. We've now got more powerful GPUs in a dedicated cluster, and they can use that. Like I say, these systems came in 2013, so they're getting old now. And so modern GPUs are just more efficient.
Is there an upgrade path? Like,
yes and no. Yes, you can. Not without changing the hardware, which I'll come to in a minute. For these, yes, you can go a little bit. These Galaxy has Ivy Bridge CPUs. If anyone knows their Intel CPUs, Galaxy has Ivy Bridge. Our login nodes were still Sandy Bridge, but then we upgraded Magnus to Haswell, which was at the time the upgrade about 6 years ago.
Yeah, it was HUDC at the time.
Yeah. So we've got a shiny supercomputer, but we still need login nodes, file systems, software, and accounting, power, cooling, and some way of dealing with users. So file systems. So we have a lot of disks. This is a Cray badged enclosure, but you can see it from other vendors. And when you're loading in disks, this is one of our Cray guys. You can tell by the shiny blue jacket. They all have shiny blue jackets. You get a special tool to load in 6 disks at a time, which when you're doing hundreds of them is useful. We use a system called Lustre, which is with scale-out storage for the HPC. The cloud team use a product called Ceph, which is again another scale-out storage. Rather than trying to have a couple of massive disks, we just keep adding enclosures of disks. Home still runs good old NFS because it works. So Lustre is what we use for our file systems. Basically you have a metadata server which says who owns the data, what it is, how big it is, where it's stored, and they tend to run on a couple of really fast or SSD disks. Everything's designed to fail over, so you'll have different, 2 pairs on your tails. So if you've got SAS disks, you plug it into 2 systems at once, so in theory it falls over cleanly. The software is designed to run on either node, and you run HA, so it can swap over between them if you shoot one node. The disk servers themselves have either Ethernet or InfiniBand on. They just plug into your Fabrics connection. And then, depending how many disks you want or how fast you want it to be, you just keep adding storage nodes. So this object store, for our fast system, we have 40 disks per node. It's basically 82 disks in an array, which 82 disks, it's 84 plus 2, including 2 SSDs. They're not shared between 2 servers. It can fail over. So we've got 14 of those for our Scratch file system. Gives the performance about 70 gigabytes a second. Yes, that is 2 Blu-rays a second. It's fairly fast. But to get that, you have to be able to write. You can't just do that from one node. You have to have a job that's accessing this. And then you're back to, have I got a fairly large file network that can take that traffic, burst in, and so on. Group, which is where we store all our software and longer term, like Scratch, anything on there, as the name suggests, is volatile. We delete it, it hasn't been touched after 30 days. Users have an unlimited quota, not strictly to, they can only create 1 million files. And yeah, 1 million is not enough for some users. But anything's not been used for 30 days gets deleted. Group, they get an allowance on that that's quoted for the length of their project. And the 2 Astronomy users have dedicated file systems because they need certain performance. So ASKAP in particular, they have a pipeline that involves data coming down from the telescope, needs to be written quickly to disk, and then they can process it from there. So they have a whole 16 nodes just for ingesting the data. They're just split into 4 by 4. Each one has a 10 gig link into that cluster. They run a job that processes it and writes it out to disk. If you want more, you open your checkbook and just order more boxes. You can run interactively, but when you've got thousands of nodes, you'd leave it up to some other algorithm. So we use batch schedulers. We use a product called Slurm, which is basically an open source one. It's what the big labs are using. You need to find something your vendor's happy supporting as well. The user basically prepares a script, submits to the scheduler finds a gap that fulfills the number of nodes they need, the wall clock they require, and at some point mails you the error log. If you're lucky, your job's actually run, but yeah. Users are not very good at estimating how long their jobs run. Some are, because they can say, I need this number of nodes. Well, actually, I need between this number of nodes and this number of nodes, and I need it to run for 7 hours, 27 minutes. And they can say that, 7.5 hour job, and it'll fit that in. Our default maximum time that people can run jobs for is 24 hours. So you get users who go, I don't know, but say I need 24 hours. But then the system's trying to find them a 24-hour window. If they know their job's going to be 27 minutes, they just ask for half an hour, and it can go, I've got a space coming up, I'll fit you in. So it runs backfill to try and fill in the gaps. It's like giant Tetris, basically. The actual software for high-performance computing, you pretty much need a dedicated staff. And that's where supercomputing centres stand out. Yes, you can have you can go to Azure and pay, and you can run on a Cray in Azure. But unless you've got it optimized, it's going to hurt your checkbook fairly hard. You can also go to Amazon. They don't do Cray, but you can get some fairly good HPC resources. And then you start finding that I talked earlier about MPI and OpenMP, that difference. You've then got all your different libraries, which maths library you're using. You find that one's not compatible with your program, but you need this for something else. And the versions, to try to have a support matrix you can actually work with, is a nightmare. So Magnus is getting old. We have had a nice fat checkbook. So our new system, which is our test development system, should be coming in May, with delivery later on in the year for the main phase 0, which is basically 2 cabinets will replace those 8 cabinets that we had earlier that we can cut our users over to, and then expand up from there. So since we ordered it, I think, Cray got bought out by HPE, and their previous branding of Shasta is now an HPE Cray EX system. and it's going to be 50 petaflops, so substantially faster than Magnus. It's about 30 times combined of Magnus and Galaxy. 200,000 cores for CPU and 750 AMD GPUs. AMD are not exactly known for their GPUs at the moment, but we're not the only site getting one of these things. So yes, we're getting a 50 petaflop system, but it's the same architecture that the Americans are using for their big exascale ones. So all the R&D and getting all the compilers optimized, etc., are being done by Uncle Sam with his very deep checkbooks. So hopefully this will help us. 548 terabytes of memory, which is quite a lot of RAM sticks. And it's 10 times more efficient than the system we have, so hopefully it'll keep the vendors happy, the people who pay the electricity bills happy. But even so, we need to upgrade our plant to, we need 2 megawatts in the compute room.
Lower cooling requirements as well? About the same? About the same,
I think, well, it's 2 megawatts of heat.
Yeah.
So it's 4 times what we've got at the moment.
Ready odd, basically.
Yeah. So I talked about the Dragonfly and so on for the interconnects. Cray had this thing called Slingshot, which is their next generation, that allows you some more flexibility. It doesn't have to be 16 devices plugged in. It's Ethernet based. This is a lot of heat sinks on those. Although it uses Ethernet, it's got a low latency. 100 gig now is available on the cards for our test system, but we'll be doing an upgrade to 200 gig for the next system, for the upgrade. And so this is what it looks like. Lots of cooling. You basically have a cooling unit at the end that takes your water supply for your system through a couple of heat exchangers, pumps, etc., to pump it around the rest of the system. And so each of the front nodes has little water hoses for your blue and your red, for your hot and cold, and basically you just stack them in. It's very similar, but it gets you the density on an engineered form rather than being the pile them high, sell them cheap stack of cloud hosting. So that's why you go to a nice big vendor, because they do have engineers who design these things. And I'm running out of slides. So. Radio Astronomy, we basically at Pawsey support 2 big projects. The MWA, which will become SKA low, with a substantial increase in requirements for what they do, but that's to be decided between Pawsey funding and the SKA consortium. We're also looking after ASKAP, which is the Pathfinder, and they have these nice steerable dishes. I'm going to play a video because the clever bit on the SK is the radio antenna itself, the receiver, and hopefully this will work. Here's a little CSR video.
Since humans first looked skyward, the star-filled heavens have been a source of constant fascination and amazement, inspiring us to better understand the cosmos as well as our place within it. Australia's CSIRO has long supported this quest for understanding, developing innovative technologies for radio astronomy, a key science that allows investigation into the complex history of the universe. For more than 60 years, our engineers and technicians have worked together in developing leading-edge technologies needed to receive, amplify, and process the cosmic radio waves that travel through the incomprehensible distances of space. A key challenge facing radio astronomers is the limited region of sky that can be seen by conventional telescope receivers at any one particular time. Now, we've developed a revolutionary new receiver, the Phased Array Feed, or PAF, that will address this challenge. It will open up an antenna's field of view and increase survey speeds by more than a factor of 20.
The Phased Array Feeds will revolutionise all of radio astronomy by offering us the opportunity to view a large part of the sky all at once and to survey the entire sky very quickly and repeatedly. We'll just be able to get a totally different perspective on the universe that we're a part of.
We're opening up a new area of technology with this innovation. It has this ability to operate over a very large frequency range with full sampling of the electromagnetic wavefront. It combines electromagnetics, electronics of low noise devices that are embedded into this antenna, and also real-time digital signal processing. There's no receiving technology of this form at the moment, and it will enable astronomy programs that would take 10 years to be completed in a matter of months.
Certainly it's attracted people already to Australia through the Square Kilometre Array program, but well beyond that, the other applications and the spin-offs of the technology include medical imaging of the human body, security and surveillance applications, and a whole range of other areas. And that's a challenge that an engineer just loves, because it's cutting-edge new research and it's practical.
The PAF will transform the way we survey the sky and have a major impact, enabling breakthroughs in the way we understand the universe.
Let's have some nice footage of the shots of the telescope. That's the reason I included it. And that is it. Any questions?
You're talking about the Ivy bridges and all the GPUs and CPUs and all that sort of stuff, and that sort of reminded me of all these microcode updates that have been needed doing in recent times. Does that have a dramatic impact on?
Yes, it can do. The risk we take with a lot of our stuff is we go, yep, we know users can potentially do bad stuff. It's a closed cluster of users that we run on our systems, so it's a risk we take, but we turn off some of the stuff on some systems. The cloud systems, no. Yeah, if we let Joe user run stuff on their system, we'd need to lock them down hard. The other systems, we take the risk, and we know, because they say we're not going to do anything bad, we can go after them, because it's a smallish community. Yeah, 1,600 users is a lot, but that probably comes down to 300 or 400 active users at any one time who are really heavily using the system. So yeah, it's just a risk.
Is there any triage that's done on like what they want to run, what researchers want to run?
Not at an operational stage. Like, they can put on their application, we're going to do this code, run something completely different, but then they can't. We monitor the system and go, something's funny with that node. We tend to see nodes that are out of whack fairly heavily. I'm not sure whether. So I'm going to try dragging this up. Hopefully it's going to work. Not while PowerPoint's open. And show. Where is it? Put the second monitor. Well, finds the other monitor. Looks promising. No. I was hoping to drag up the dashboard. That one of the things I use just for keeping an eye on the system. Oh, there you go. Come on. So this is 7 days worth of plots. So we can generally see what's happening on the system. And so you start to see load spikes, especially on this one. If I just do, you can generally see when the system's draining to let large jobs in, we see the power go down. Although it's small on each cabinet, because they start to stack up. We've got 8 cabinets on Magnus. I can tell that that's a large job going in, because we can see the speed. It's probably, I think this is 50 kilowatt. 1, 2, 3. Yeah, these would be 50 kilowatt axes, so it's probably a jump of 40 kilowatts when that job started in our power usage. So you start to see anomalies. That's looking at the site as a whole, but we can drill down to nodes and jobs and pull off a lot more stuff. It's going to be hard to drive because it's such small resolution. I'm going to try and find another one.
So presumably that drop is more like sort of loading data in or whatever, just getting this up ready for the job to spin it.
This is what I was talking about back schedulers. So probably someone said, I need a job that takes 300 nodes.
Yeah.
And so the system goes, right, that job's finishing, I'll start to hold those. I've got a small job I can fit in, but it ends up with a gap. So our overall resource usage is high, but you see it'll drop down from being like 98% full down to about 80% full and then back up again.
Is it dynamic enough that if for some reason you've got, I've been working in IT for 20 years, so if you've got a job that runs for say 12 hours, but it's supposed to run for 24, but then terminates early, is it then intelligent enough to try and schedule something else in?
Yes. Every scheduling cycle, it just starts afresh. So if it's suddenly finds it's got 100 nodes free, it'll go, right, what can I fit into 100 nodes? This isn't a problem for us because we only normally have a couple of thousand jobs in the queue. The big sites like NERSC, their scheduling runs used to take minutes to go through their tens of thousands of jobs, where it tries to work out. And then you start to put things like in, right, only look at the first 200 jobs of each user, and then anything after that we ignore, or like if you can't resolve it in a certain amount of time, it can go through. So the whole art of scheduling is a whole PhD subject in itself.
Andrew, how much involvement do the vendors have in this? Like, if they got people on site?
Yeah. So we have several Cray systems, and our maintenance contract includes a body on site. Yeah. When you get a new system, you probably get a couple of bodies. As you start to get better and better, you can pay more, less, I'm not sure, to be trained up yourself to do some basic parts replacement. But Paul's really good. I mean, we've got a fantastic vendor engineer on site, and we've been really lucky with our vendors. So, I can't fault them. There's been times when they've had to do a part replacement across all the systems for some reason. For an upstream vendor of theirs has changed some spec, and they've gone, no, we have to replace all of component X, bring bodies in, get the table set up, pull a card, swap them out, and they've done that in like no time. We've also had like entire disks replaced in a whole storage array, and they just get the bodies in and do it.
And I assume most of that is hot swappable stuff.
If you've got to physically pull cards out to replace memory DIMMs, that sort of thing, components die. So memory DIMMs do fail, and so what we have to do is, because of the layout of the system, we have to drain 4 nodes, pull the card out, replace them. CPU dies, he swaps them over, is it the motherboard or the CPU? So all that sort of basic engineering triage, he just gets on with.
So I noticed it's actually reporting that in Jira as to what's faulty.
Yeah.
At the time, I just went, oh, okay.
I'm intrigued with the water cooling system. Is that fairly reliable? You showed tubes and things running there everywhere. Do you end up with water leaks and issues when you're changing cards? Or?
No. I mean, I don't think I've got any photos of the back. Let me see what we've got on our public website. Pawsey. The Crays themselves are close coupled. They don't ever get unplumbed. They run on a 22-degree loop. That's dedicated. Pawsey's clever in that we've got a groundwater system. So basically we have a couple of boreholes. There's 2 aquifers in Western Australia. There's the general one that people use to water their lawns, and then there's a lower one which I think is called a Mullaloo aquifer that's deeper, and so we have an injection borehole on one side of the site, an extraction borehole that we can pull in, and from memory I think it's something like 26, 27 degrees the water comes out at. So when we're putting 30-degree water back in, obviously it's through a heat exchanger, so we're recycling the bore water, and we end up with 3 layers of heat exchangers. So we've got the heat exchanger in the system, the cooling loop, and then the injection loop. The commodity computers, which is like the clusters or storage, they all run on 16-degree radiators on the back of each rack. So you have normal Dell server type things that blow air into a radiator on the back of each rack door. Most of the new ones we're putting in, we have full door radiators, so we can open the door. Our older system had a very good close coupled system with 4 radiator panels on. It was nice and tight, and you had to remove it, but they beat your fingers, something rotten. there was a metal gap. You had to unplug the hose coupling. So if anyone knows SGI D-racks, I have some choice words to say that's probably not for broadcast. But yeah, you didn't leak water. We'd get a couple of drips, but like a J-cloth is fine for that, as long as you do it in the right order.
And what data formats are there? Like, when you get something, what actually is the data?
Depends on each code. So there are packable formats that are designed for multiple systems writing to the same file, things like HDF5, which is like a structured layout on the disk that each part of the program that's running and by each node knows it writes to a certain point on that file, so it doesn't overlap. But we do get users who are not used to running multiple process systems, so rank node 1 to rank node 100 all tries to write to a.out, not a.out.rank. And so yes, they wonder why they've only got one output file instead of 100. But the actual what's on that disk, it's just a POSIX file systems, whatever they save their stuff as. Our new system's going to be using S3 bucket type storage for our medium term. This is how a POSIX scratch file system, but when people come to write files for their longer term projects, they have to get used to like an Amazon S3 type bucket that they throw their data into, which could be interesting. We have users who have got PhDs in programming down to, oh my god, what's this weird command line interface? I've never touched a computer before that's not drag and drop. And that learning curve from how to run your first job on a supercomputer is huge. It's not quite as bad as running your first job on the grid, because you don't have to worry about certificates, but the whole, how do I SSH into something? What does SSH mean? That connection is a big issue for some of our users. Universities don't have a basic half-rack cluster for a lot of researchers. You can do a hell of a lot with like half a rack of kit. If they could do that initial training on site and then they know their code works and scale up, it would be easy, but then it's probably harder to justify the staff we have. So you've got to train from both ends.
Supercomputing 101.
Yeah, pretty much. We do an introduction to supercomputing course.
It was fun to watch my wife when she went for a PhD, and she had her first experience going from a Mac to actually using the AE supercomputer.
Yeah.
And there was this absolute panic for about half a day of what the heck, because she could get SSH or remote shell into command line, and then no clue about what she was doing. Now she's running scripts like you wouldn't believe. It's second nature.
Yeah, I think users don't care what their system runs on; they just want to get the science. Yeah. And this is the problem. I'm the sysadmin of it, so yeah, you can keep your comments about sysadmins, but for me, just running the service is a challenge. But the users don't care; they just want their science.
Dare I ask about quantum computing?
You can, but I missed the presentation. So
No, I just, from the point of view, that's obviously on the horizon, and there are a lot of vendors coming out with semi-commercial sort of solutions. Is that sort of being talked about? Is that in the pipeline? Is that...
Come on, drag up. And here's one I prepared earlier.
Oh, there you go.
Yes, very much so. Oh, careful, it pulls the mic cable. So, Pawsey is doing a lot of work at the moment with a new room temperature quantum system that we're hopefully getting installed real soon now. Yes.
Okay.
But I can't go into details because I don't know. Not because I can't go into details, but because I just don't know.
No.
There is some public stuff available on our website, which is pawsey.org.au, and it's in the news section.
Cool.
There was a presentation by some of the folks involved in it a couple of weeks ago. I'm not sure whether their video is archived. If not, I can get our PR people if people are interested.
And in fact, that's a good plug for Pawsey. Have a fairly active YouTube channel with a whole lot of information about the sort of the publicly accessible research that's available and worth a look, because we've run a few videos here on an ATV night around it of the sort of research that's being done and the computing that's being done. So very interesting. Worth a look. Any final questions for Andrew? Can we show our appreciation? Thank you very much.
Welcome.
Grab a coffee and ask any further questions.
So, how long in Australia?
What's that?
How long?
Have I been here? Came here in 2013.